In this example, we're going to be finding some eigenvalues and corresponding eigenvectors. We have ourselves a 2 by 2 matrix by the name of A. First row of A is -2, 4. Second row of A is 1, 1. So the first thing we're going to do is set up the characteristic polynomial of A, which of course would be the determinant of A minus lambda I. Or if you prefer, you could also do the determinant of lambda I minus A. No harm, no foul there. Now, when you're setting these up by hand for yourself, my recommendation for you is set up your main diagonal first. Reason being, those entries are going to be a little extra wide with the extra minus lambda associated with them. Then fill in all of your other entries. Otherwise, you're going to wind up with a matrix that's probably too narrow. Now, multiplying for this 2 by 2 determinant, first we multiply our main diagonal entries together, -2 minus lambda and 1 minus lambda. And then we'll subtract the product of the entries along the other diagonal. Now, if you're looking at this and thinking to yourself, F that, you are absolutely correct. We do want to FOIL that out. So first is going to be -2 times 1, -2 times negative lambda times +1, and negative lambda times negative lambda. Then we'll tag on a -4 as well. Combining all of our like terms and remembering to actually write down the square on the lambda square, and then rearranging so that the polynomial is in descending order, we will get lambda squared, looks like plus lambda, minus 6. Now the characteristic equation is what we get by setting this equal to 0. So for the characteristic equation, that'll be lambda squared plus lambda minus 6 is equal to 0. Looks like this one's going to turn out pretty nicely because this does factor pretty nicely over the real numbers. We'll get a lambda plus 3 and a lambda minus 2. Setting each of those factors equal to 0 or applying the factor theorem tells us that lambda equals -3 and lambda equals +2 will be our two eigenvalues. Now to come up with the corresponding eigenvector, we will need to actually set up A minus lambda I times the eigenvector is equal to is equal to the 0 vector. So given that we're dealing with a 2 by 2 matrix, we'll set up a two-dimensional vector. For lambda equals, let's start with our positive value, +2. We'll be setting up A minus 2i times v is equal to the 0 vector. So I'm going to head back to this matrix here, and I'm going to plug in lambda equals 2. Or simply go back to the original matrix and subtract 2 from all entries on the main diagonal. The -2 will become -4, and +1 will become -1. The other two entries will stay the same. Augment with the 0 vector. We notice that these two rows are indeed multiples of one another, which is exactly what we want to have happen. Taking this into reduced row echelon form, which you should be able to do without a calculator, we'll go ahead and take, we'll swap the rows and then add 4 times this row to 0 that row out. Then we'll have a 1, -1, 0. Now the eigenvector is going to be any non-trivial solution of the resulting equation. Now what I'm getting out of that first equation is that v1 minus v2 is equal to 0, or we can interpret as v1 is equal to v2. Now again, you're allowed to pick any non-trivial solution. So what I'm going to do is go ahead and set one of these equal to 1 so that the other one will be equal to 1 as well. That'll give us eigenvector for lambda equals 2 is the vector 1, 1. But really any non-zero scalar multiple of 1, 1 would work as well. For lambda equals -3, this time we're going to be setting up a minus lambda I minus -3 times I would be a plus 3i times vector v is equal to the 0 vector. So this time, heading back to this matrix right here, I'm going to be plugging in lambda equals -3, also known as adding 3 to the entries on the main diagonal. That will turn this into 1, 4, 0, 1, 4, 0. Very obvious that we will wind up with a row of zeros by taking -1 times the first row, adding to the second row, And by an amazing coincidence, that is going to wind up being reduced row echelon form. We can interpret this as v1 plus 4 times v2 is equal to 0. Or simply v1 is equal to negative 4 times v2. v2 is acting as our free variable here. We're allowed to set it equal to whatever we want. I'm going to recommend that we just go ahead and use 1 for that free variable. That way we'll get v1 is equal to negative 4. So we set v2 equal to 1. We got v1 is equal to negative 4. And I don't know why I wrote that as a column instead of as this. Really, I suppose that they're kind of synonymous in R2, aren't they? Well, regardless of how you want to write it, we'll give some purpose to these things in the next section.